Boston Museum of Science with Daniel Davis, the program manager for live presentations. And we're in the Theater of Electricity. So tell us a little bit about what we're looking at here.
Well, Dave, it's a pleasure to welcome you to the Elihu Thompson Theater of Electricity. Elihu Thompson was a co-founder of General Electric and a benefactor of the museum. And the theater is dominated by our 37-foot-tall open-air Van de Graaff generator, which we're lucky to have because not only is it one of the largest of its kind in the world, it was also built by its inventor and namesake. Robert Jameson Van de Graaff himself oversaw construction of the machine behind us from 1931 to 1933.
So what can a Van de Graaff generator tell us about electrostatics?
Well, a Van de Graaff generator is really a mechanical charge pump, and it does much more efficiently what was first done in 600 BC by a Greek named Thales of Miletus. In fact, our word electricity comes from the Greek word for amber, fossilized tree resin, in Greek electron, because when Thales rubbed amber up against fur, he discovered a force between the two. Now, rather than using amber, I actually have a plastic hoop here, and there's charge in everything in equal amounts, positive charge on the inside of every atom and negative charge on the outside. Now, both kinds of charge make the electric force, and each makes it the opposite way. Normally, the charges are in equal amounts, one sitting on top of the other, so that the pushes and the pulls cancel and the electric force goes unnoticed. But when we put different materials in contact, in this case, whenever I put the fur in contact with the hoop, the fur becomes positively charged and the plastic ring negatively charged. Now, charges are invisible and silent, so we don't see their effect, but if I take a Mylar hoop, it's initially attracted to the ring, and then when it acquires a negative charge, the same charge is on the ring, it's repelled by the ring. So we see that like charges repel. Now, what a Van de Graaff generator does is, instead of having someone mechanically rub different materials together, it uses a motor. So here I have a handheld Van de Graaff generator, batteries, a small motor, and a rubber belt. So in this case, negative charge is taken off of this stick, pulled off by the belt, and then put into me and into the ground, leaving the stick positively charged. So there we see I don't have to rub anything, but now the hoop is positively charged, as is the stick. Now, if you recall, our plastic hoop is negatively charged, oppositely charged. So it's attracted to the hoop until it acquires a negative charge itself, and then attracted to the stick, and then pushed away. So there we see charges of opposite type are attracted to one another, and charges of like type repel. With our larger Van de Graaff generator, again, we've got a motor and a belt. In this case, it is negatively charged, so positive charge is left behind in the ground. Negative charge goes on a rubber belt here inside this plastic column, and a motor spins the belt around to pull the negative charge on it further from opposite positive charge in the ground. And it's the work that the motor does against the force of attraction between the negative charge in the belt and the opposite charge in the ground that increases the energy of those charges or their voltage before they're collected here on this metal sphere.
So how fast can you throw them with this thing?
You can throw them near the speed of light. And so the closer you approach the speed of light, the heavier the particles become. It's a relativistic effect, so that's a hard limit, but nearly the speed of light.
How is this Van de Graaff generator different from the big guy?
Well, you'll notice that the large Van de Graaff generator has two spheres, and that's because originally it was two separate generators. In a balloon hangar in South Dartmouth, Massachusetts, where it was originally constructed, one machine was charged positively, the other negatively, and an accelerator tube put between the two so that one generator could push the atoms, the other could pull the atoms, so you had twice the accelerating potential. When it moved to MIT in roughly 1938, the two spheres were fused together because in that configuration, all of your measurement equipment had to be isolated up inside one of the terminals. They didn't need as high of accelerating potential, so they fused the two spheres. They took the charging belts out of one and then put the accelerator tube down the empty column. It was used to produce X-rays in that configuration, and that's the configuration we got it from in 1955. So the leftmost column is empty. That's where the accelerator tube was originally housed, and the rightmost column is the one that has the charging belts. All right, so instead of accelerating atoms, we're going to be accelerating some Rice Krispies. And so the first thing I'm going to have you do is I'm going to have you step on this insulating column so that the charge that builds up on you doesn't recombine with the opposite charge in the ground. And I'll have you put your hand on this metal sphere so that the charge that's collected on the sphere of the Van de Graaff also is conducted onto you as well. And I'm going to have you hold out your left palm, and I'm going to pour some Rice Krispies in there. And I'm going to have you gently close your hand. I'm going to turn the Van de Graaff generator on so that you're negatively charged as well as the Rice Krispies. And then I'm going to have you gently open up your hand and flatten out your palm as you extend your arm, so we'll see what effect all that negative charge has on the Rice Krispies and you. You ready, Dave?
I'm ready.
All right, here we go. All right, extend your arm and open up your fingers. So all the charge on the Rice Krispies is repelled by the like charge on your palms, demonstrating that like charges repel. So if you reach out a knuckle, then we'll see that even though you don't seem to be charged, those charges are invisible, they were silent, but whenever you came close enough to me, the negative charge on you was neutralized by opposite positive charge that came up from the ground into me. That neutralization probably wasn't complete.
Ow.
Got another one, but that one was considerably smaller than the first. And if we do it again, nothing.
Back to
good.
normal.
So now the balance is restored, we're back to normal. So we're going to put the charges on the belts and pull the charges further from opposite charges in the ground. Those charges are going to collect not only on the sphere, but also on you. And we'll see what happens when we have all the charges on the hair and you. So I'm going to hold this mirror up so you can see what happens.
Here, look at the mirror.
So all the charges on your hair are pushing away from the charges on your body, showing us that charges of the same kind repel or push away. Now I'm connected to opposite positive charge in the ground, so if I bring my hand near your hair, it's attracted to my hand, and yet it's pushed away from itself. So opposites attract and likes repel. So watch what happens when I bring my hand near your hair. Your hair is attracted to my hand, and then it's pushed away from itself. Gently shake your head side to side like you're saying no. Keep shaking. All right, now forward and back like you're a rock star. All right, toss your hair back and take a look.
I like that hairstyle.
Because I'm connected to opposite positive charge in the ground, if I bring my hand near your hair is attracted to my hand, and yet it's pushed away from itself. So that we see that opposite charges attract and likes repel. So breakdown voltage in air at atmospheric pressure for very small gaps is about 30,000 volts per centimeter. And at that electric field strength, electrons acquire enough kinetic energy in between the space between molecules, the mean free path, that they obtain an ionizing potential amount of kinetic energy so that when they collide with the neutral atom, they liberate more electrons that then are accelerated to cause more ionization, and make an avalanche. And so for small gaps, when we achieve this, then it's enough to break the air down and make a spark. And so we see that there's more rapid sparking whenever the gap is smaller because the Van de Graaff can charge up to small potentials rapidly. The farther we go away, the more time there is between discharges because the Van de Graaff charges with a constant current, and it takes a longer time to build up to the higher voltage required to break the air down. Now, even though I'm being struck with tens of kilovolts, multiple tens of kilovolts, because the amount of charge is so low, the overall energy is small enough that it's not harmful. So voltage is the energy that each charge has, but to know the total energy, we have to know the number of charges too. So even though the voltage each charge has is really high in this case, because the number of charges is so small, the overall energy is certainly not dangerous. It's kind of like dropping a grain of rice from the top of the Empire State Building on your head. Even though the height is high, the amount of mass is really small, so it's not harmful. But if you stuck your finger in a wall outlet, that would be a different story, because there, even though the voltage is lower, the amount of charge available is much higher. So that's like dropping a bowling ball on your foot from the height of your knee. May not be a really high height, but the mass is large, or in the electrical analogy, the amount of charge. So there it can be dangerous.
So the museum's famed for its lightning shows. Any chance our students could get a peek at that?
Absolutely. We'll pull all the stops out using not only the giant pantograph generator, but also our Tesla coils and musical Tesla coils. But as you're aware, it's quite loud, so you're going to want to cover your ears.
All right, safety first, kids. Thanks so much, Daniel. It's been great.
Truly, my pleasure, Dave. Thank you.